And these nanoparticles, of course, are below the 100 nanometer scale and probably of a few nanometers scale. So they are very much they are more and more used now since the beginning of the century in catalysis. And when you are making drugs or any imported molecules in pharmacy, of course, you have to ask yourself the problem of how this molecule is being made, and do you have any trace of nanomaterial that is toxic, like nanoparticles, and this problem has not been addressed very much so far. So if you look at all these transition metals which are located here, everybody knows that osmium is toxic, but now we are talking about bulk metals and not about nanoparticles. Concerning nanoparticles, it's probable that all the nanoparticles are toxic. Gold may be an exception, because gold is so far recognized as being non-toxic for normal cells, at least as far as now. So the problem is to try to get a way to the toxicology of this nanoparticle. So looking more carefully at nanoparticles, very often, I would say most often, the organometallic chemists and catalytic chemists are using mixed materials with two different metals, because they are efficient, they are more efficient. So what are these materials? So they can be particle in particle, they can be particle on particle, they can be aggregated particle, core shell, alloy, separate particle, supercore shell, etc. So this gives you an idea of the state of bimetallic nanoparticle catalyst. So the only, I would say, transition metal that is said to be non-toxic by, I would say, all the studies, all the scientists who have been looking at the toxicity toward normal cells, is gold. So, of course, gold is a reputation of being non-toxic as bulk, but gold is very special as a nanomaterial, nanoparticle. And so far, nanoparticles have a reputation to be non-toxic, but gold 1 and gold 3 are toxic. So the problem is the following: when you are using gold nanoparticle, are you going to generate a gold 1 and gold 3, which have some toxicity? So here we have an example of the use of gold nanoparticle as a template. Gold nanoparticles are very, very practical. They are great use, and most gold nanoparticles have thiolate ligand. That is to say, you use a thiol, you introduce the thiol, you lose the hydrogen, and you have a thiolate ligand. So these are very robust. You can evaporate solvent, you can get them in a condensed state or in solution. So they are very much used and very famous now. And we have been using this gold nanoparticle to encapsulate anti-cancer drug, and this is a taxane, docetaxel, which is the most important anti-cancer drug so far, which is in use, which is commercialized. But the big problem is that it is not soluble in water, and you need to inject on patients in aqueous solution. So the way to overcome this problem is to encapsulate the drug into a material that is water soluble. If you decorate the nanoparticle with water-soluble periphery, polyethylene glycol, then it becomes soluble in water. And then you can use these nanosystems in nanomedicine eventually. So the way it is synthesized from the tetrachloroauric acid, and then you introduce the thiol as a thiolate on the gold. Then you exchange, this is non-functional, then you exchange the functional chain, then you continue to functionalize, and then by reaction between the acido and the alkyne, the very well-known click reaction catalyzed by copper 1, you can introduce a functional group which is a polyethylene glycol to solubilize the system. So this is the synthesis. Of course, you have gold-free at this level here, which is toxic. So you have to be careful the toxicity of the starting material. Then this shows you the system in water. So this is NMR at 600 megahertz in water. It's not in dehydrated water, but in real water. But to have a lock, you need to introduce dehydrated water in a capillary to be able to lock the system and to record the NMR in water. So this is the NMR of the drug in the DMSO, and this is the same system in water. So you can get a water solution of a compound showing that you have succeeded in the encapsulation. Well, these nanoparticles are non-toxic to a normal cell, completely non-toxic, as I already mentioned. But they are toxic for cancer cell. You can see that they are 2.5-fold more toxic than the drug alone. So it means that there is a benefit of encapsulating, of course, the drug into this water-soluble nanoparticle, and you have benefit for attacking the cancer cell with this system. So if you address the synthesis of a more complex system, here the gold nanosphere, they are not simply nanoparticles, they are nanospheres. That is to say that there's an empty cavity, and they have been designed by the group of Alas in the United States. And then you can coat these gold nanospheres with iron oxides, and iron oxide, but iron oxide are toxic. So you want to use iron oxide for the thermal therapy against cancer cell, because it will kill your cancer cell, but then you want to remove the toxicity of iron oxide, so you have to coat this iron oxide shell with a silica shell to get a super shell system. And these are the shape of the system. So you really have to design a complex or elaborated nano strategy in order to avoid the toxicity of the iron oxide in this case, and in any toxic particle in general, using nanoscience. So the great advantage of gold nanoparticle is the imaging, and this imaging is important for diagnostics. So there are a number of imaging techniques which are modern techniques which are in use now for diagnostic using gold nanoparticle, various gold nanoparticle, two-photon luminescence, confocal microscopy, scanning electron microscopy, dark field light scattering, photoacoustic tomography, optical fluorescence tomography. So these are very modern, sophisticated techniques, but all deal with gold nanoparticles. Some of these techniques deal with quantum dots as well. Quantum dots are toxic, gold nanoparticles are non-toxic, so there is an advantage at this point on gold nanoparticle. So this is an example of the use of gold nanoparticle as sensors. So this is a way to synthesize a gold nanoparticle starting from gold tetrachloroauric acid. So you can use thiol, so linear thiol, dendronic thiol, and in one step you make a dendrimer which has a nanoparticle in the center, and this nanoparticle can be used for ATP sensing using a redox sensor here, in which the silicon, which are in blue here, can bind oxygen to have a weak bond, which will interact with the ferrocene system, what has a redox potential that will be changed by interaction in the supramolecular system. So the way to make nanoparticle protected by dendrimer can be twofold, actually. You can have, with small dendrimers, you can have stabilization of a large nanoparticle, because you cannot make the nanoparticle inside the dendrimer. So you are going to have several dendrimers surrounding a large nanoparticle. And here, if you have a large dendrimer, then it is possible to encapsulate a small nanoparticle. So depending on the generation and size of the dendrimer, you can make a very small nanoparticle of the order of 1 nanometer to large nanoparticle of the order of 50 nanometers. So all the scale between the two is accessible using the dendrimer technology. For instance, you can repeatedly react the dendrimer with tetrachloroic acid, reduce the gold free to gold zero, and then repeat again to load a large amount of gold nanoparticle inside the dendrimer. And this has been done by this research group. You can also use the surface plasmon bond, which is the basis of all the diagnostic technology that I have shown before. And just to give you an idea of the plasmon band, the plasmon band will have an electromagnetic frequency of this magnitude, and this will induce a resonance which is in a coherent oscillation with the free electrons of the metal. It's a box, it's a small box of electrons, which is like a quantum dot in the gold nanoparticle. So gold nanoparticles are quantum dots, and the plasmon band, which is in the visible region, is very important and is extremely sensitive to the size, to the nature of the metal. You can do it with silver also. To the shape, you can see different shape here, different size. And this great dependency is used for diagnostic in nanomedicine. And you can see here the variation of the wavelength of the band depending on the shape, and also on the shape from number 1 here, which is in the visible region, which is globular, to number 5, which has a large ratio between the length and the width. So when you have these dots, you can move the visible region. You can move the absorption from visible to the infrared, and the infrared region is, of course, more useful in nanomedicine because you can go deeper inside the skin in the case of cancer, which are up to almost 1 centimeter depth inside. So here you see what happens if you reduce gold tetrachloroic acid, and you have a purple line for the gold free. If you coordinate the ligands in the dendrimer with gold free, then you have a UV visible band which is almost the same. So the blue here is almost the same as the purple. It's still gold free. When you reduce to gold zero, then the gold zero has the visible plasmon band. Here you can characterize the nanoparticle in this way. So the dendrimers can allow you to generate the nanoparticle. The small dendrimer, G0 generation, allow you to get a large nanoparticle. When you are larger than, say, 3 nanometers, you are in the solid state. So you have a plasmon band which is visible. And when you are lower than 3 nanometers or 2 nanometers, say, then you are in the molecular states. So you do not have this quantum dot plasmon band. So you can recognize at once that the large dendrimer encapsulates small nanoparticles, which are smaller than 2 nanometers because they don't have this plasmon band. And this can be checked by transmission electron microscopy, TEM, or high resolution TEM, which is a major tool for nanochemists to characterize the nanoparticle. And you can see here that the dendrimer of 0th generation encapsulates large nanoparticle, 4 nanometers, and that the first and second generation encapsulate small nanoparticle of 1.9 and 1.8 nanometers. One last thing I would like to say about gold nanoparticle is catalysis. In the late 80s, the discovery by Masatake Haruta in Japan was very important when he found that gold nanoparticle coated with some oxide, can be a transition metal oxide or main group oxide, are able to be a very good catalyst. And even so at minus 80 degrees, which show that gold can be extremely reactive when it is in the shape of small nanoparticle. And this very important reactivity was discovered if the nanoparticle is smaller than 5 nanometers. If it is larger than 5 nanometers, you don't get this catalysis. So you can see here the dependence on the size of a nanoparticle. If it is larger than 5, there's no reaction. If it is smaller than 5, and it is very reactive. So then this is able to oxidize CO to CO2, which means that if you start your car in the morning, normally you have a platinum in your pipe, so the platinum will not be able to oxidize CO at room temperature. So in the first minute, you are polluting. But if you had gold nanoparticle in your pipe, then that would be oxidized immediately, even at low temperature, so you will not be polluting because you will have CO2 immediately. So anyway, this also tells that gold nanoparticles are extremely reactive, so one should be very careful about the potential production of gold 1 and gold 3, which are probably much more toxic than gold 0 nanoparticle. And catalysis deals not only with oxidation, but also in a number of reactions which have been discovered in the last quarter of a century. So this means that gold nanoparticles now are going to be increasingly used in catalysis. You can see the production in terms of publication, which is becoming very high in the catalytic field. So these scientists will have to be concerned with the toxicity issues because they are always dealing with nanoparticles which are coated with oxide. And in this case, it is probable that at the interside between the gold and the oxide, you have gold 1 and gold 3, which are generated. So I am at the end of the talk. I would like to summarize the message. So the toxicity of metal nanoparticle will concern small nanoparticle, but small nanoparticle are produced in synthesis, in catalytic reaction, in material science, especially in nanomedicine, so one has to be careful. And the toxic metals are now being combined by nanoscientists with organic or bioorganic materials in order to protect the toxic nanoparticle with non-toxic organic or bioorganic material. So one has to make sure that the protection is efficient. So there is a lot of work in this supramolecular approach. And then the last message is that gold has a unique function among transition metal or late transition metal in being non-toxic, and there is a lot of issues and a lot of work on working with gold nanoparticle in nanomedicine for both therapy with, for example, the photothermal therapy, and the diagnostic with all the imaging technique which I have shown you using the surface Plasmon band. But of course, last but not least, you have to mine gold 1 and gold 3. So this is the research group, quite international. Alison Francois did the cancer cell work. The catalysis work was done by Abdou Diallo, Leon Yang, and now started by Christophe Dered for his PhD. And this nice girl did also some work. And I would like to thank you for your attention.
Thanks a lot, Didier, for this nice presentation on nanotechnology, supramolecular chemistry, hybrid material. And it's also a very good example of safety by design. You have shown how by designing at the nanoscale you can tune the properties and the toxicity of the nanomaterials. So questions? We have some time for questions. No? Well, just one question. How stable is stables are the dendrimers, and how fast they can degrade in a body? Do you know?
How stable?
In a body, how stable they degrade at cellular level, for example.
How stable? Which one?
Dendrimers.
Well, I didn't speak about the toxicity of dendrimers, but again, dendrimers can be toxic or non-toxic, and that completely depends on the periphery. That is to say, for example, if you have cationic periphery, ammonium, phosphonium, and so on, then there is the study show that there is a relatively important toxicity. For example, for the transfection, you find toxicity, and that's a real problem. So people have been trying to bring anionic termini, carboxylate, for instance, and the anionic termini are considered as non-toxic so far, or much less toxic. So then the dendrimers, like all the polymers, have probably some toxicity problems, but you have to be very careful at what is at the periphery, and the periphery will define the solubility, the toxicity, and a lot of the function of the dendrimers.
No more questions? We thank the speaker again.